Hello everyone and welcome to the Rancho Mirage Library and Observatory. My name is Eric McLaughlin. I'm the astronomer for the Library and Observatory, and I want to note something before we get going. Our programming here is actually funded through our Library and Observatory Foundation, so if you're interested, please consider looking into our Library and Observatory Foundation, and if you're interested in helping make programs like this possible, please consider donating as well. Now today we're going to be talking about red dwarfs, and as you might note with this particular title, it's actually a play on an old sailor's phrase that goes something like this. Red sky at night, sailor's delight. Red sky at morning, sailor's warning. But with regards to a red dwarf, the question then becomes, what if that red star is just up at what you call noon, and therefore we can actually have, in some sense, a red sky at noon. And what does that mean for life itself? So we're going to take a look at red dwarfs now, but before we can actually talk about red dwarfs and the possibility of life around them, we have to ask the question of what is a red dwarf star? And really the only way you can talk about it is just by looking at size and color. And if you look at this diagram here in the lower left-hand corner, you can actually see a bit of small red stars located there. What that area is referred to as is where you would find red dwarf stars. But there is no exact definition for what a red dwarf star is. That exact cutoff on color or brightness is not exactly well understood or even intentionally defined. But the big thing to note is that they are significantly less massive than the sun, and the important thing with that is the lower the mass of a star, the cooler it actually burns, thus making it more red. Now, it's also important to note that the lower cutoff for a red dwarf is, while not clear-cut known, we have a fairly good definition for it at least. It would be where fusion at the center of a star stops, because a star is powered by nuclear fusion at its core, fueling everything on that main sequence. That center line there is powered by a process which fuses hydrogen into helium. Now, below about 7 or 8% of the mass of the sun, somewhere in that range, that stops, and thus you end up with a different category of objects at that point. So red dwarfs, that definition would stop somewhere in that area. So, all right, well, important to know, are these types of stars common? And yes, very yes, they are extremely common. Our galaxy is thought to have between 100 billion and 400 billion stars as a general estimate. And by looking at the population near us, we find a lot of red dwarfs very close by. Thus, we actually can estimate that the population of red dwarfs in the galaxy may account for 80% of the stars in the Milky Way. So 80% of those numbers is what you would actually be talking about for the number of red dwarf stars in the Milky Way Galaxy. Okay, well, that's good to know. Well, if we know that there are red dwarf stars, are there planets around these stars? Yes, we actually find them quite frequently, and the way we would do that is by using radial velocity measurements, basically measuring the Doppler shift. If you're not familiar with the Doppler shift, what that is it's associated with that sound you hear when a car drives by, the old that actual change in pitch of sound is the Doppler effect. It works for light as well, so if we actually watch specific features of the light coming from stars, we can actually measure their velocity moving away from us or towards us. Doing that, we can actually watch periodic oscillations of a star that tell us whether or not there's something orbiting around that star. Likewise, we watch for planetary transits, which is a planet moving right in front of a star, and that causes a very brief dimming of that star that we can measure using even fairly small telescopes. So we've actually been able to find quite a few of these planets around red dwarf stars, and it's interesting to note that when we find them, they tend to have lower mass on average than planets we find around sun-like stars. In other words, we don't find as many big old Jupiter-type stars around red dwarf stars, we don't find Jupiter-like planets around red dwarf stars. Instead, we find things that are typically, on average, a little smaller. But there was an interesting survey done with the HARP spectrograph down in Chile on one of the European Southern Observatory's telescopes, and by doing a survey of a variety of red dwarf stars, they were actually able to determine something really profound. And that is that around 40% of red dwarf stars will have something called a super-Earth in their habitable zone. Now, there's two things to define there. Super-Earths basically are planets that are a bit more massive than the Earth, but not a lot more massive. So they're referred to in that sense as super-Earths. But the other thing we'll define in a second is habitable zone. The other thing to note is that 40% number, it is the best estimate, but the range of estimates go all the way from 25 to 95% of those stars. So there is potential for still a lot to an extremely a lot. So that would be an important thing to note. But about that habitable zone word, that is a very important thing to define. What it is not the space around a star where every planet there will be habitable like the Earth. That is not what that means. It does not mean that anything lying in this space will be Earth 2.0. Note that when you ever hear any news about planets discovered in habitable zones, it is not a way of saying this planet is habitable. It's a way of saying that something else might be going on there. In particular, what it means is that the orbital distance from a star, it's the orbital distance from a star where a planet similar to Earth would actually be able to have liquid water on its surface. So if you took the Earth and put it in that zone around that star, liquid water could potentially be on the surface of that body. However, it's not well defined. We really are saying a very general estimate when we say that, and it's really not a guarantee of anything when we're talking about it. So it's worth noting that this is a really just a barely baseline thing when we're talking about it. And when we actually talk about other factors involved in it, we really can't say that we can detect an Earth 2.0. So again, if you hear news stations or any article talking about the discovery of a planet in the habitable zone of another star, it's not going to necessarily be Earth 2.0. If they say it's a habitable planet, no, they're mischaracterizing that statement at this point in time. So it will be a long time before we actually have that true capability. And a way to actually talk about the resolution we actually need, there's another scale for talking about how Earth-like a planet is. And if you put Venus on that scale, it comes out at a 9 out of 10, really. Normally they do 0 to 1, but I just did 0 to 10 to make it really clear. So we're saying that Venus is very, very close to the Earth in its actual type from the observational characteristics we can actually get here. Now, if you know anything about Venus, you know it's not a good place to have your next beach vacation because the surface of there is incredibly inhospitable. The temperatures are hot enough to melt lead. The pressures are 90 times that of the Earth. And when we've sent space probes to the surface there, the longest any of them have lasted is about 2 hours before they break. So 9 out of 10 doesn't say anything, really, when you're actually talking about habitability. Nevertheless, it's one way to actually say we have something that's very similar. So if we're actually looking at the habitable zone here in our solar system, this is what we're looking at. You can actually see Venus is right on the inner edge of what would be considered habitable. And all the way out on the other end of it is where Mars is. Both these planets are not places where you just want to go and without a spacesuit or anything ridiculous. So ridiculously good protecting. And as such, it's important to note that the habitable zone is really a very, very, very rough guideline. So keep that in mind as we pursue forward to find Earth-like planets here and find out whether or not we can find a good place for life around red dwarfs. So moving right along, all right, how many planets actually exist in the habitable zones of red dwarfs? Again, doing a little bit of math that we were talking about there, we take that 100 billion, multiply it by the 80%, and then the 40%, that comes out to 32 billion habitable zone planets around red dwarfs in the Milky Way Galaxy. Add in a lot of uncertainty and other things. At the very least, you can say there are 10 to the 10 exoplanets in habitable zones in the Milky Way on that order of it, and that is 1 with 10 zeros after it. That is how you would get that number out. So again, that doesn't mean they're all places you can go visit and take off your spacesuit and go swimming. No, it doesn't mean that. But it is something that is a good starting point. So with these statistics, it's a notable thing to say, well, maybe such worlds might be nearby where we can actually try and further characterize to find out if it's a place we can actually go visit. And when I say close by, of course, I'm meaning astronomically speaking. Close by is a really relative term. So what am I talking about close by? Well, I'll talk about the pale red dot campaign. The pale red dot campaign is named after the pale blue dot photo that the Voyager spacecraft took where the Earth was only a single pixel that was blue in color and pale. In this case, it's referring to Proxima Centauri, which is the Sun's nearest stellar neighbor. It is around 4.2 light years away, and it's quite small. Now, what the Red Dot campaign did is it tried to have a truly open access science campaign. In other words, they were daily posting things so people could actually interact with the science team directly to see how it is one goes about finding a planet around another star. Now, what they were actually able to do is successfully discover a planet around Proxima Centauri, that close star. And the nomenclature for actually giving a name to a planet around a star is what you see on the top of the screen there. You have the star name and a lowercase b for the first planet you discover, lowercase c for the next, and so on and so forth. If you see a capital letter there, that is another star. So if it's in this case, Alpha Centauri can be talked about in a few different ways. Another name for Proxima Centauri is Alpha Centauri capital C. It is the third star in that system. Granted, they're very far apart, so it's not like everything's all mixed together there. All right, so what other things are going on with this particular star? Again, it's Proxima Centauri. It is around 12% the mass of the sun, and it is actually very faint. It is too faint to be seen with the unaided eye, and it is about 15% the size of the sun, or again, around 1.5 times the size of Jupiter. So again, it's very, very small compared to our own sun, and that also means it's very, very dim. If you look to the chart down on the right, you'll see a number of things that were actually noted there. The actual discovery of Proxima Centauri came in 1917. Again, the closest star to us was discovered in 1917. And then a couple of further ones out, which are not quite red dwarfs. They're a little bit lower mass, way out here. Those two were discovered back in 2013. So our local neighborhood, again, local being a term used relatively here in astronomy, it really is a place we don't know all that much about, and we're constantly finding new things. But yeah, so we found a few things there, and one other thing we found that was really interesting about Proxima Centauri is that it is actually what is called a flare star. Now, what does that actually mean? Well, to actually describe what that means, we have to take a look at the interior of that star. So what we're actually talking about with stars that are significantly smaller than the sun or less massive than the sun, in particular, those that are about 35% the mass of the sun, they do have an interesting set of properties. First and foremost, the entire interior behaves differently. Our sun has a radiative core. The core is actually doesn't have very much material moving through it. It radiates a lot of heat into a convective layer. But in a star like this, the interior is fully convective, and that may not really make that much sense to you, but we can actually talk about it in terms of a lava lamp, where a lava lamp is a great way of talking about the way convection works. You have a heat source down at the bottom, and it causes the wax in it to actually liquefy and float up to the top, where it cools off and sinks back down. That is a particular motion due to convection. And when we're talking about a red dwarf star, the bottom of the lamp would be akin to the center of the red dwarf star, while the surface of the lamp would actually be akin to the outer layer of the star itself. Again, the top of the lamp, I should say. So that is what we're talking about with fully convective. That means the entire interior of the star is actually having material moving through it in a long but very worthwhile process. It's worthwhile because it's one of the reasons that stars like red dwarfs can actually burn for over 1 trillion years, because they can actually take all of their material, keep it moving, and always have new, fresh hydrogen at its core to fuse into helium. It never gets a huge buildup of helium at its core, unlike our own sun, which will get a big old core of helium, at which point fusion has to change. But we're talking about red dwarfs now, so again, that convection ensures hydrogen burning into helium goes on for the entire lifespan of the star. Now, what's important to note is that fully convective stars are expected to not have very efficient stellar winds, which is very important to note because stellar winds are what cause the rotation rate of a star to actually decrease through a loss of angular momentum. You can actually think about this in the reverse of what you see with regards to a ice skater. When you see an ice skater and they're spinning around in circles and they pull their arms together and they spin even faster, that is the result of what is called conservation of angular momentum. What we're seeing here in the stellar wind is actually the reverse. It's the material of the star actually getting blown off over time, and as such, the star itself will slow its rotation rate. Why does that matter? Well, it matters because stellar rotation is directly related to surface activity. This is all a preview for next month, by the way, where I'll be talking about the surface of the sun and all sorts of things with regards to space weather. This is really related directly to what I'll be talking about there. But again, stellar rotation is associated with surface activity. Thus, if you have your low-mass star not able to lose angular momentum, it means it will spin rapidly for a very long period of time, which will actually cause very active surfaces. So hopefully I didn't lose you on that train of thought because I put the mesmerizing lava lamp over there. Hopefully you're still with me. All right, what am I actually going to say with this? Well, again, I mentioned Proxima b has been characterized as a flare star. And so the surface of Proxima b, or of Proxima Centauri, is very active. And in fact, on almost exactly a year before we actually opened up our observatory here, a stellar flare was detected on the surface of Proxima Centauri, and it actually increased the brightness of that star by 1,000 times. So that is a very important thing to note because, yes, we found a nice little planet orbiting around that star in its habitable zone, but it's habitable at a stable point. If you have something actually being incredibly fluctuating in its brightness, well, that might cause some problems. In particular, that planet would have received around 4,000 times the radiation that the Earth gets during solar flare events. So the stellar flares on Proxima Centauri might actually be a very important thing to note. So again, when you're looking at that type of thing, it's what leads people to believe that we might actually have a scenario more like this, a very, very active star. And by that I mean you see all these sunspots and everything. And if you look closely at that little planet down in the lower right, you'll actually see it has a tail to it. The thought is that these very active stars might actually be powerful enough to blow off the atmospheres of anything in their habitable zones. So the question then becomes, is red sky at noon really a sign of life's doom? Well, in other words, do such flares and that highly active environment, does it destroy the atmospheres of those worlds? And actually, quite possibly. When we actually try and model these environments, what we will see is that we can actually see that these planets might not have a long enough period of time to really have a good amount of life on their surface. They might actually lose their atmospheres, or at least lose enough of their atmospheres to become inhospitable. However, for higher mass red dwarfs, ones that don't have a purely convective interior, they can actually potentially have good stable systems which could offer a time for which life may form or persist on that planet be much longer than what we would expect even for our own Earth. So there might be an optimal star out there that might be around 55% of the sun's mass, but again, it's important to note that as we go up, there are other models that suggest other things, including the fact that at those levels, you might actually have higher UV light, which could be working to inhibit any life on their surfaces. Finally, it's important to note with all these models, though, these are really in their early stages of development. Most of what I'm talking about here is actually stuff that has been published this year. So the science is still really working on this to actually try and characterize what we're talking about with regards to the way stars, red dwarf stars, interact with their planets. Why is it so new? Well, because Again, that pale red dot campaign was just a couple years ago. It was just a few years back, and so this particular subject hasn't really been in the forefront of astronomical thought. So making these modeling ideas is still worth doing. Now, there's another factor that's really important to note with regards to planets around these red dwarf stars, and that is that they can become tidally locked, and it's actually expected that those in their habitable zone likely would be. What does that mean? Well, what that means is it's similar to the way our own moon, if you ever look at it, its surface doesn't appear to change because it doesn't appear to be rotating with respect to our perspective. What that means is the same face of the moon is always facing the Earth. Likewise, planets around red dwarfs will likely have their one side of the planet always facing the red dwarf star. So you have one side potentially getting absolutely scorchingly hot and the other side outright cryogenic. So you might actually have a point where it would be boilingly hot on one side and on the other side so cold that the atmosphere itself might condense out. So how could you actually have a nice stable place for that? Well, one way you might actually get that to work is if you have a very large ocean on that planet. If you actually were able to convectively move a lot of that heat, or just have just some general circulation causing that heat to be distributed around that planet, that would make a huge difference in the habitability of these worlds. But there's another thing to note about that, and that is that you would actually potentially have a place where you would have perpetual sunrise and sunset. And what I mean by that is the best place on a world that has a good amount of heat circulation that is tidally locked might be near the point where you actually have the terminator, the difference between day and night. So you could hang out where you have sunrise and sunset, but let me state that more clearly. Starrise and starset on those planets. You might actually be able to have what is often referred to as the twilight zone, or a ring world, where there's one area where it's nice and comfortable, but you go right underneath where the star would be right overhead. It might be too hot. You go to the other side of the planet, still might be too cold to be comfortable. So you'd end up with that sort of ring world idea. What would that actually look like? Well, here's an idea of that going along the lines of having, again, here's our red sky at noon, because you won't have the sun actually moving through the sky. It will always be in one part of the sky. And if you have a good amount of clouds, it might make them all look a nice red, the same way we can even get red clouds here during sunrise and sunset. So we can actually potentially have our nice little red sky at noon through that. But moving right along, though, does that actually give us a better possibility for it, having those caveats? Or is the tidally locked setup really something that rules out a lot of good opportunities for life there? And with that, along with the other things we've been considering, should we really be looking at red dwarfs for our planet hunting and studying missions? Well, it turns out that a lot of people have actually taken those ideas and they don't look at red dwarfs nearly as much for looking for life-harboring planets. Now, instead, what they've been looking for are single stars like our sun. Again, stars can actually come in binary or multiple star systems, so they look for ones that are by themselves, not orbiting around each other, and they're looking for these types of ones that are similar to our own sun. There are a few reasons for that, and they make good sense, because we have a fairly good idea of how at least one of these types of stars behaves. We can see the sun, and we can see it's very stable, and we can learn a lot about it, can see it very high resolution, and learn a whole lot about it. But there's other reasons. These types of stars like our sun, are at least quite a bit brighter than red dwarfs, so it's easier to detect the actual stars themselves from a greater distance. We've actually been able to find stars that are hundreds or thousands of light years away using these types of stars as a reference point. We've been able to find planets around them. But important to note is we're really at a point where our technology is almost capable of detecting Earth-like planets, that is, Earth-sized planets, orbiting in a distance from those types of stars similar to our own orbit around the sun. So having that actual setup is very important, because if we wanted to find a true Earth 2.0, we need to find something that's very similar in all of its characteristics, something around a sun-like star, something Earth-sized, something orbiting at an Earth-like distance, around 150 million kilometers from its host star. So that's one of the reasons why people have leaned towards that. And in fact, one really important survey satellite being launched is the TESS satellite, Transiting Exoplanet Survey Satellite, and it is actually working on surveying the entire sky. Now, it was just launched earlier this year, so they're working towards the science phase of the mission, but they aren't quite there. And what it's looking for are those transiting planets. If I'm the sun, it's a planet that goes right between me and you. So that is what this satellite is looking for, but it's actually intended to focus on near and bright stars. Again, I mentioned a lot of the nearby stars are actually red dwarfs, so it will see a few of those, but for the majority of its volume, it will actually, its search area volume, it will be looking at stars that are brighter than red dwarfs. It won't be focused on red dwarfs for that reason. So again, ultra cool red dwarfs like Proxima Centauri, those would be too dim beyond about 40 light years, so those won't be a huge part of the survey. But again, Proxima Centauri is actually close enough, but the planet around Proxima Centauri doesn't actually transit, so we'll kind of lose out on that one. But it's actually likely to find thousands of stars by actually looking at these star systems, so it makes sense why they would do something that requires brighter stars for this particular mission. Because again, they want to survey the entire sky, the entire volume of space really near the Earth. So it's a very worthwhile mission, and it's moving forward quite well. It's, again, was launched earlier this year, functioning well, but they're working towards the science phase. Now, it's important to note, though, that these results have not caused everyone to stop looking. There's a great group out there whose team is called TRAPPIST, which is the Transiting Planets and Planetesimals Small Telescope. Again, they sort of cheated with their acronym because TRA comes fully from transiting, so they didn't do just the first letter of each one. But it's important to note, though, that again, this is a small telescope setup. It's led by a team from the Liege Observatory. I apologize to anyone who actually speaks that language. I'm sure I completely brutally pronounced it. Yes. Anyway, but this particular team, they're working with a pair of robotic telescopes that are actually around 0.6 meters in diameter, and this is where I find it really nice and interesting. This particular team, their telescopes, they're a little bit smaller than ours, so that means we could actually potentially do similar research to them using our own setup here. Now, what have they actually been looking at? Well, or rather, why are they actually interested in ultra-cool red dwarfs? Well, the important thing to note is that, yeah, these small, dim stars actually make the detection of planets, transiting planets, easier because the planets that pass in front of their stars will block more of the light, and they will actually be able to be characterized a little better by actually being able to look at their atmospheres and such, because again, more of the light from the star ends up being blocked. Now, as we talked about the differences between these planets and our own setup here, it actually makes these a worthwhile thing to look at in and of themselves, because again, while there are some similarities, there's such worthwhile differences that studying these planets might actually teach us a lot about planets in general and planetary systems in general. So the big question then is, what have they actually found? And in fact, they found a really interesting system. Back in 2016, they actually published their first discovery of 3 objects around what is now often referred to as TRAPPIST-1. It has a few other designations, but I'll call it TRAPPIST-1 because it's convenient. And after that point, during that year, a variety of other observatories started looking at that star along with a number of space telescopes, including Spitzer and the Kepler Space Telescope and the Hubble Space Telescope. All 3 of those were spending time looking at this particular system. And in 2017, there was a really cool announcement that they actually found 4 more planets around that particular star. And even Google was really into this particular discovery. They actually put up this nice little animation here where you could actually, yeah, they were nice and happy about it. But yeah, that was actually on the front page of Google for a good while there. So I would leave it going, but it would loop forever. So we'll go right on there. Wait for the moon to be really happy. Yay! Okay. All right, so this was a really great discovery because when they actually started characterizing things, as I mentioned earlier, you don't find very many gas giants around red dwarf stars. So they found that the majority of these 7 planets are known to be rocky, and they're waiting for data on the other ones. So there's a good chance that all of them will be rocky. And a number of them actually orbit in the habitable zone of that star, so that gives even more than one chance for something to be relatively nice. Again, that definition being so incredibly loose. But it's some interesting things to note. The star itself is around 8.9% the mass of the sun, which comes out to around 93 times the mass of Jupiter. So it's notably more massive than Jupiter, but really it's just barely above that limit of being able to actually fuse hydrogen at its core. And the interesting thing is it's notably more dense than Jupiter because while it's 93 times as massive as Jupiter, it is only 1.2 times the diameter. So it's quite a notable thing there. But that's enough words. Let's take a look at it in another way. This is a nice diagram to actually show it. You can actually see on the top, this whole section up here is to at least a radius scale. The orbits are to scale, where you have Jupiter and the star actually in comparison. The orbits of Jupiter's moons would fit almost inside the orbit of the innermost of those planets. But if you actually compare this to the solar system, note that everything up here has been increased in size by a factor of 25. All of this orbit of these planets would fit there. So again, that is Mercury. If these planets were all around the sun, they would be so fried. It's not actually the case, though, because we actually have, again, a much cooler star. It's emitting a lot less light and radiation. And as such, if we compare the actual habitable zones here, we can actually see something that looks a bit like this. Again, we saw this earlier. So when we're looking at this setup here, good old D through G have some interesting possibilities for the habitable zone. But again, there are some interesting definitions and other factors that make that green area not sufficient to really talk about those particular worlds. So, all right, we've learned quite a bit. But in 2018, we found out some other interesting information. And I'm going to let some of the team members there tell you about that.
In February of 2017, astronomers wowed the world with the discovery that a total of 7 Earth-sized worlds orbited the faint star known as TRAPPIST-1. Now, a year later, we have learned that they are all rocky planets, and that some of them could potentially have hundreds of times as much water as Earth. But you might wonder, how can we know this about planets we cannot see directly and that orbit an ultra-cool star 40 light-years away that itself is barely bigger than Jupiter? It's possible, due to the very special layout of this system, together with extended observations by NASA's Spitzer Space Telescope, working in conjunction with Kepler, Hubble, and a collection of ground-based observatories. Astronomers can detect planets around stars by carefully watching for tiny, repeating dips in brightness. If orbiting planets are lined up just right, when they pass in front of the star, they block a tiny bit of its light. The amount of dimming gives us the planet's sizes, and the timing tells us about their orbits. This kind of observation has been done for thousands of exoplanets. But to understand what the planets are made of, we need to know their densities, which means we have to measure their masses very accurately. That's incredibly hard, but in the case of TRAPPIST-1, not impossible. If a planet orbits a star in isolation, it's like a perfect stopwatch, with every orbit ticking off an exact period of time. However, adding another nearby planet messes this up a little bit. The mutual gravitational pull between the planets will speed them up or slow them down in different parts of their orbits. The timing is no longer perfect. If we observe the timing variations of the planets over many orbits, astronomers can, using a lot of math, calculate just how much mass each planet must have to create these schedule glitches. It turns out that the TRAPPIST-1 system is ideal for this kind of measurement. The planets are so close together that they have particularly strong gravitational effects on each other that create noticeable variations on the order of a few minutes. Spitzer is particularly sensitive to the infrared glow from ultra-cool dwarf stars like this one. To date, it's devoted over 1,100 hours to accurately measuring the transits and timing for this system alone. Combining that data with a Kepler campaign and ongoing observations from many other telescopes has enabled the most precise measurements of mass and density ever made for a system of exoplanets. So, what does this tell us about the TRAPPIST-1 system? To start, let's see how the rocky planets in our own solar system stack up by size, density, and solar illumination. Now we can add the TRAPPIST-1 planets and compare them. You might first note that while TRAPPIST-1b is a bit on the warm side, C is a pretty close match for Venus in all of these properties. As far as this study goes, they're nearly twins. TRAPPIST-1e is almost the same size and density as Earth, and while it receives a little less illumination, it still gets more than Mars. It's not hard to imagine that, depending on its exact composition, it too could have oceans on its surface. Between them, TRAPPIST-1d has about the same illumination as Earth, but is smaller and less dense. Theories of planetary composition suggest that up to 5% of its mass could be in the form of water, possibly covering it in an ocean vastly deeper than any deep-sea trench found on Earth. The outer planet densities are a little higher, but still low compared to Earth. This could indicate significant amounts of water, probably more in the form of ice as they get colder. Remarkably, we now know more about TRAPPIST-1 than any other planetary system besides our own, and we are still learning more. Hubble has been able to rule out puffy, hydrogen-rich atmospheres around 5 of these planets so far, strengthening the conclusion that they are rocky and potentially rich with water. With the upcoming launch of the James Webb Space Telescope, astronomers will be able to make even more detailed studies of the atmospheric chemistry of worlds like these. NASA's upcoming TESS mission will likely find thousands more systems. And Spitzer will remain a powerful complementary tool for studying small planets around small, cool stars like TRAPPIST-1.
So once again, an important thing to note there is that we've learned more about this system of planets than any other in the universe besides our own solar system. So it's a really wonderful thing to actually be looking at this and learn that there might be planets that could, based on their densities, could have up to 5% of their total mass be water. That is not insubstantial. The vast majority of the Earth's mass is, again, actually rock and iron and other things there. There's just a really fairly thin layer of water all around the outside surface. So when we're actually looking at these particular places, think back to what I talked about earlier with regards to heat motion around a planet. If we have a tidally locked planet, if it's actually covered in an ocean of water, it might actually be able to distribute that heat well. Again, more than one of those planets might have actual liquid water on it. So it's a good thing to note. So then, does that mean based on these things, should you actually plan your next beach vacation for the TRAPPIST-1 system? Well, at least someone at JPL likes the idea because they made a nice poster, Planet Hop through TRAPPIST-1, voted best Hab Zone vacation in the galaxy. So it's a nice, fun little idea, but will that actually play out? Should you actually try and go there? Well, if you have a way to get there, let me know, because I want to actually just know how to travel that far. But it's really important to note that there are really too many unknowns at this time still to truly characterize this system down to a point of saying, this is a place we can go and we can sail around on the surface and whatnot. Now, we have some good ideas, but we still need to learn a lot more. So really, you should keep an eye out on the news for interesting discoveries with regards to this system, because as they mentioned in that video, 1,100 hours for one space telescope to just be looking at one star system is incredibly unusual, because that is a lot of time to spend for a space telescope where there are very few of them looking at one star. So you can imagine that it's a nice, important place, and there might be more things for us to discover there. So this actually brings us a little bit back to where we started. Red sky at noon, life's boon or life's doom. We can't fully say for sure, though a lot of the general modeling does suggest more on the doom side. So we really might not expect to find a lot of really nice places. Nevertheless, there are still extreme numbers of unknowns, and when we actually look at what we have here with TRAPPIST-1 and Proxima Centauri b, they are really important laboratories where we can actually go back to those models that say, oh, those places won't be habitable, and we can actually test those models. Again, if we expect there to be no atmosphere around the stars or the planets of TRAPPIST-1, then, well, if we find a huge ocean, does that mean the models were wrong? Well, not necessarily. We just have density readings right now. But if we do actually find more to say whether or not there is an ocean there, that could be really interesting. Nevertheless, we have these two systems. If we really characterize them a lot, dig into them, and find out a lot of answers to our questions, then we might actually be able to use that information on other ones. And again, when it comes to the statistics of it all, there might be places out there. So when you're looking at these two, if they don't turn out to be good for habitability, maybe we could look elsewhere. Again, that would just be 2 down and 10 to the 10 to go. So we have a lot of different places we can look in this galaxy to try and find a lot of other information. So we should be excited and just keep on looking not only at red dwarfs, but all the other stars out there as well. Thank you.